Hello, Year 11. Welcome to a couple of introductory videos on programming and the concepts around programming, how to get set up with Pascal, and how to put everything together. I'm going to give you some introductions that we did a couple of weeks ago for the students that were in class. So if this is not new to you, then just stick with it. You might get something extra out of it. If you were not there a couple of weeks ago, then this is what we went through. But obviously, I can't be physically in front of you to teach you to you again. We're going to start out, as it says on the screen, with the concept of algorithms. At the core of it, making software, writing software is about writing algorithms, fixing problems, and developing solutions to things that are going on. So we're going to start out with making algorithms. In this video, I'll walk you through how that works, the pseudocode, flowcharts, and IPOs. Then I'm going to step you into actually preparing your Pascal environment, how to actually set up Pascal, where to get it from, and those sorts of things. I'll also walk you through the introductory concepts of programming, what these programming concepts are very, very briefly. And then I will produce an individual video on each of those in Pascal and how to use them in Pascal. Pascal is important because your first assignment is going to be on Pascal. Your major project next year is going to be in Pascal. Pascal is a language very similar to the pseudocode, and the pseudocode is what all your assignments, your exams are going to be in. So this is one of those areas that is very important for you to gain an understanding of. So walk with me as we look at algorithms. So algorithms, how do we make software? At the core, software is designed to solve a problem. If you have a problem that there is something that needs to go on, you use software to develop a fix or to assist with a fix. Software obviously can't do everything. There are a wide variety of different things that it can do. For example, as I've said here, if you want to produce a letter with a letterhead, software is a good choice because you can program up an actual design, you can have your logo, you can have names, you can have places. That's a good start. If you want to get from Albury to New York City in America, why you'd want to do that right now, I don't know. But if you want to do that, then software is not the best solution for that per se, but it assists with the best solutions. Your best solution is to make a plane. Not many of us can fly a plane. How do we then get to New York City? We program a piece of software to fly the plane for us, right? We can go and build a commercial jet, and then we can use software to actually take us from point A to point B. So software helps us to actually understand how to break these problems down. However, regardless of whether we're doing a software solution or not, there are some tools that we will use to be able to develop these solutions to problems. These are known as algorithms. Algorithms help us to solve the everyday problems that we have in our lives, regardless as to what those problems are. The two most important diagnostic tools that we have in this way are known as flowcharts or branching diagrams and pseudocode. These are two forms of algorithms that allow us to take a complicated problem and break it down into its smaller and smaller parts. Now, an algorithm is sort of like a mathematical formula. If I write up here, for example, 3x equals 15, then we know from our mathematical study that we can take 15 and divide it by 3, and the answer will be 5. Therefore, x will equal 5. That is a simple little way of using an algorithm to break down the problem. We take our issue. We need to find out what x is here. We know what our result is that we want to be, and we know what the conditions are that we can use. We then take our result, divide it by our conditions, and we get an answer. Therefore, we can make a conclusion on how to solve this problem. The solution to the problem, x is equal to 5. Algorithms work in roughly the same way. Algorithms allow us to take complicated issues and break them down into smaller and smaller parts so that we have a final solution to whatever the particular issue is. We can produce a solution that helps us to understand. Flowcharts are a very good example of this. We have these as the three main objects in flowcharts. There are some more in your books and in your notes, so you can go through and find them yourself. But these are the three primary ones we use. The oblong circle with rounded edges is known as a terminator. This starts and stops the program. Generally, programs have one start and one end. Some programs, as we're about to see, don't have an end because they repeat indefinitely, but every program will have a start condition. Sometimes in these, we write conditions in for what we want the program to start in. For example, if you are running a program that then calls another program, you may send it some information, right? You might send it a letter, and you might have that letter be a condition of the start. This really should be more of an oblong, so we'll just shrink that down a bit here. These are instructions. These are things that actually happen in the program. So when we give a command to the program, that's what we're doing. Here, for example, turn on a light. And diamonds are seen as decisions. Now, the advantage we have of diamonds and decisions in flowcharts is there's no difference between simple decisions and complex decisions. We can have a decision with simply two options coming off it if whatever this condition is met, yes and no, or we can make this more and more complex. We can make a whole bunch of different options using a list of statements. We don't want to overcomplicate it with language, but in program, these are known as switch and if statements, but we'll come to that in a moment. When we take flowcharts like this and we put them together into a structure, we then can explain things a little bit more clearly and a little bit with a lot more detail by using what's known as pseudocode. Pseudocode is where we use simple words and simple statements and commands to flow out whatever the information is, whatever the problem is. Now, I gave you the example, which was a bit of a ludicrous example of how to make a cup of tea, how to make some toast. Those sorts of things are really useful to us, and I suggest that you continue to do that, which I know some of you have been doing. Continue to do that with your everyday lives. But when we actually look at the flowcharts, we can make these a little bit more simple by using our flowcharts as examples. Let's have a look at one. For example, here, we have here a start terminator. This is going to start our program. We're going to set up whatever that means, whatever our equipment is going to be set up in this particular case. And then we're going to read a button. Now, this is actually from my year 7, so the context for this is an Arduino setup, a little circuit setup, and we're going to read a button. What is the condition of a button? Then we're going to ask a question. Is that button pressed? We have a button. Is that button being pressed right now? Simple little button. It could be anything. It could be a key on a keyboard, button on a mouse. It could be a light switch anywhere. Is that button being pressed? If that button is being pressed, if we say yes, the button is being pressed, we follow through this arm here and we turn on a light. That's it, right? If this button is being pressed, we turn on a light. We then continue this flow down on this particular channel, and it goes back here, and as you can see, it loops up to read the condition again. So this is an infinite loop. This will never be ended, and that's the way that Arduino code is designed. This will continue. However, if the button is not pressed, then we go on this arm, and we turn the LED off. And then when that is off, we again come back down to this infinite loop. These little joiners are used sometimes. Some people use them, some people don't. I like to throw them in because it makes my code easier to read. But that's the simple little question. That is a flowchart for simply turning a light on from a button press. Very, very simple piece of code. Now, as that reads, however, there is a lot of questions about this. So that's why we go to the next step and we actually write the pseudocode for this same thing. So I'll zoom out a touch more so we can see this. Now, we start off with our start, but the thing with pseudocode is we're only looking at the instructions inside. This is why both flowcharts and pseudocode work so well together. In our pseudocode, when you say setup, we don't need to care what the setup is. The setup is already done for us. In our flowchart, however, we give an opportunity for that to happen. In our pseudocode, we don't care about reading buttons and things in. It's not until we get into really complex positions that we actually need to start looking at variables, which we'll talk about in a moment. But generally in pseudocode, we ask simply about the condition of situations. We don't want to start getting bogged down with programming terminology. However, we do want to use simple questions, so we do use some programming terminology. It's one of those little ironies that we'll see here. For example, we start up, we don't need to care about any setup, and we don't need to care about reading the button because we really don't care what the state of the button is. We only care about what the state of the button is. We don't care about actually taking a reading here. We only ask the question. So we start and we say, if button is pressed on. Notice here I've got a lot of words in capital letters. Start, if, is, on, then, turn on, etc. These are because they are commands. They are parts of the program that are very, very strict and deliberate. If button is pressed on. So very, very specific language. If that button is pressed on, Then we will turn on a light. Now, notice I've got an indent here. This is important because it shows me where that if statement sits. We will turn on the light. Don't care which light it is in this particular case because that's what we're going to be programming. But in this case, if this button is pressed on, and sometimes you can press a button off because you have buttons that work that way, then we will turn on the light. We have an else statement. In another case, we will turn off a light. And then we'll repeat that indefinitely. That's a simple little piece of pseudocode. You don't need to ask too many extra questions. Which button is it? There's only one button on the system. Which light is it? There's only one light on the system. Why are we saying it's pressed on? Because there are some lights, because we don't want it to turn the light off when we press the button, right? Because we don't want to turn off when we're not pressing the button. We want the light to turn on when we're pressing the button. This is why it's so deliberately done. And that is a little piece of context for this pseudocode. Now we can expand this out and make it more and more complex as we go. This is another version of this same an Arduino code that again I give to my Year 7s, and this is a little bit more complex. So if we zoom in a touch here, we can see again we have a setup and a read button. So now we're going to start and we're going to read a button. But this is a little bit different. We're now going to ask, is the light on? So we start, we set up all of our equipment, and then we read a button. Read whether or not a button is being pressed. Read the state of the button. Is the light that button is supposed to turn on? So if this light is not on, no, then we ask, is the button turned on? So follow the logic through. Is the light turned on? No, it's not. Is the button then indeed being pressed? Well, yes, it is. Okay, so if the light is not on, but the button is on, then we turn on the light. And then we wait. We have a little delay in here. We're going to wait for 400 milliseconds or 0.4 of a second. So this is a toggle switch to check if the light is on and then if the button's being pressed. If the light is in fact on and the button is in fact being pressed, then we turn the light off and we wait again. And if you notice, once again, we have looped the whole thing. We've got the whole thing coming back up to the top here to our loop. So this is a pair of if statements. These are what is known as nested if statements or nested questions that are being put together just so that we can check if a light is on and then check if a button is being pressed. What does the pseudocode look like? Let's zoom out a touch. And this is what the pseudocode will look like. If the LED is on, so if this light is turned on, again, we don't need to worry about the setup and the read button, but we do want to look at the start. So we've got our start beginning. If that light is turned on, then if that button is turned on, is the button turned on? So notice we've got one if statement here and one if statement here. One question, another question. If that is turned on and that button, we could have nested these together, but we've decided not to because we've got different conditions. If that button is on, then turn on the light. Sorry. If the light is on and the button is on, we always go to the yeses first, excuse me. We always go to the yeses first. So if the light is on, yes, and the button is on, yes, then we turn that light off. So we're following our logic. If this is on and that is on, yes to off. And we're going to delay, but we don't need to worry about our delays so much in pseudocode. Sometimes they're irrelevant, sometimes they're not. However, you notice that there is no else to this if statement. Look at how I have laid this out. This is important. This is very, very important. Remember from our Python from last year that this was important. It will become important again when we do our Pascal. When we lay these statements out, when we lay these points out, you need to be able to see immediately where things relate to. If I was to delete all of this back over here, then this else statement would relate itself up to this if statement. And that would make no sense because we're then asking the opposite question. That would make no sense. However, by leaving these indents in, we can see that this if statement has this then statement and this else statement. We can follow exactly where this is going. We can follow this in detail. If this LED is not on, that then will be ignored and this else statement will be run. If that LED is not on, then if that button is on, then it will turn the light on. So we're following this logic straight through. Now, I really should have put those delays in here as well, but you can get the picture. You can see how this will flow through. That is how our flowcharts and our pseudocodes match up together. They are supposed to say the same thing. They're supposed to follow one after the other in how they are working. So After we follow those flowcharts through and our pseudocode through, the last thing which we will be doing more in our programming than we will be in the other things are what are known as IPO charts, input process output charts. They show us, they demonstrate to us the process using our inputs and using our outputs. They get a little bit more technical, a little bit more codish, but not actually codish. They show the pseudocode, and they show what the process will happen with these different things. For example, in this one, we're going to input the width and the height of something. What we're going to process is to find the area, which is equal to the width times the height. That's where we define our process. And our algorithm is then written down here. We're going to start. We're going to read the area, or the width and the height in. We're going to give them then from the user. How we do that, we don't care, because that's technical. But we're going to read in the width and height, and then we'll calculate the area of a rectangle of width times height and print that back to the user. And then in this particular example, we have an end statement. That's our pseudocode. It's nice and simple. My only criticism to this would be that I would actually have indented this, but this is a picture and I can't really edit it right now. So this really should be indented a little bit, but that's it. We read something in, we calculate something. How that calculation is done will be done in the code. We don't need to worry about that. And then we print the result back, and the output is simply the area of a rectangle. Notice again, this is very high-level language. This is very user-friendly language. Because remember, majority of times with these documents, not only are we giving them to other programmers that may not be trained in our language, but we also have to give them to managers, to people who may not know code at all, who may have no understanding of programming. So that's why we write these documentations. And as I've said in our Pascal, I want you guys to go through and write this documentation out for each of those projects. Now, I've got a couple more up on the Google Classroom at the moment. There will be more to come, but this is where we are up to. Okay, so let's have a look at some of the basics of programming. So when we start programming, what is programming? Let's start looking at the actual technical side of programming. What is programming? There are basic programming concepts to writing software. There are three principal primary concepts that any software language you find will use in some form. Any programming language that you find will have in some form. When we talk about object-oriented programming, we add a fourth concept. In Pascal, we don't have that fourth concept, which are known as structs, but we have something similar to it called functions. We will talk about that when we get there. But to give you an overview of these, variables are simply areas of memory where we can store information. That's all they are. They are places where information is put into memory, defined by memory and defined by the programming language, and can then be adjusted and used in our program as we go. For example, in our little mathematical example, 3x equals 15. Our x here is a stored location in memory that is somewhere that we don't know where is. And we put the value of x into that. And then when we do our program, the 3 and the 5, the 3 that is used in our program is already written there. So we don't need to store that. The x here is simply an area of memory, a bucket in memory somewhere that we can put information into. Now, some languages, and Pascal is one of them, require variables to be typed. That means that they are limited to a specific type of data for each variable. You cannot redefine a variable with the same name of a different type. Most languages will include integers. Integers are whole numbers. Floats, which, as we've seen in Pascal, are called reals. They are decimal points. They are portions of whole numbers. Longs are longer numbers, but I'm not sure about them being in Pascal. Chars are single characters. They are an individual letter. The letter H here is called a char or a character. Booleans are ones and zeros. They are yeses and nos. They are the most basic numbers. And strings. Now, a string is generally, and Pascal works this way too, treated as an array, a list of characters. List is the wrong word there, but an array, a brick of characters all put together that can be treated so that each of those different locations can be adjusted, but they are treated also as one variable for certain things. We'll come to that as we get there. The second basic concept are if statements. If statements are simple decisions. They are decisions that are made within the program. Right? Now, the reason that switches are not included in this list which are in Pascal, is because they're not in all languages. But if statements are in pretty much any language. If some condition is true, then code is activated. We go back to our thing here. We can see what this looks like in the pseudocode. If this LED is on, if that condition is true, then something will happen. If that condition is not true, there is an else option. There's an alternative that can play out. If that option is not true, this code will be activated on. Now, like I've done here, for different if statements that have more than one condition, sometimes it's advantageous to do what's known here as nesting. This is where we actually put different if statements underneath our original one. So we want to know if that LED is on, but the button is not pressed. Well, that hasn't been dealt with here. So if that LED is on, if button is on, that will drop a false, and then this will not happen. It will come to the end of this and it will say, well, we're doing nothing. This will all then be skipped and it will repeat. So sometimes it's more advantageous to actually nest a couple of if statements together rather than saying if LED is on and button is on, right? That can cause some errors, because what about if the button is not on but the LED is on, for example, or if the LED is not on and the button is on? If you were to have that in your condition and then you had an else here, you'd have to nest some different if statements under that anyway. So that's where if statements can be actually nested together and collected. Then we come to loops. Loops are where tasks require repetition. This is where we actually can repeat things in our programming language. Now, there are three main types of loops: while, do, and for. Every programming language will have some frame of these three loops. A for loop is probably the easiest one for us to remember. For, we define a start condition, then we define an end condition, and then we define a counting condition. That is pretty much how our code works. We are defining that this condition will go for a certain amount of time, and our something will happen in the middle. In most programming languages, this works by having the start condition be set up as a beginning of a counter, our end condition being when that end counter is met, and then our counting is simply a way of adding one to it. For example, if you wanted to compare two strings, you start at location 1, you end at whatever the smallest length of those strings is, and then you count up one by one. So if I'm comparing, for example, the word while to the word do, I will start at location 0. Location 0 is W and D. Then I will continue until I have no more characters in one of these strings, which would be the do loop hitting location 2, because there's no third character here. Loops and such will always start with the zeros. So that is how our for loops work. They loop by testing a certain number. They go by a certain number of options that can actually happen for this loop. Now, it's easy for you to break out of those. Some languages have the word break. Some languages allow you to reset this, or because this is tested at the beginning of each loop, you can simply set it up so that the end condition is going to be, after counting, more than whatever the end condition is met. So after you add 1 to the end of this loop, you make sure that end condition is met. But for loops are generally used for a specific number of times that you want it to loop through. You don't want it to loop through more than that number of times. Then we have two other types of loops. We have while loops and we have do loops. Now you'll notice that they look rather similar. But these are actually the polar opposites of what they are, of how they work. A while loop tests its conditions before the loop is run. So it will actually test and see if a condition is met before the loop is run, and while that condition is not met, it will continue to run. A do loop tests after the condition is run, right? They are known as while do or do while loops because they are test the condition after they are run. These are known as pre-test loops and these post-test loops. The pre-test loop changes. Now, I should step in here and say that different languages treat these differently. Some while loop languages actually put their condition at the end and say do at the beginning. Others will have their condition at the beginning and they work a different way. That's why they're known as pre and post test loops. I'm trying to give you the simplest way of understanding them. Sometimes these pre-test loops, will run the condition before, will run a test on the condition before any code is run. So for example, let me just write this in so that we can, oops, just want to make sure that I'm giving this as clear to you as possible. Something. A pretest will test the condition before the loop is actually run. So for example, if we wanted to have a boss fight and we step into the boss fight, but we're actually playing an old boss fight, our character is really, really out of production. It's so powerful that he walks into the boss, practically drops dead just because we are in his presence. A pretest loop would be a good idea there because then we don't need to go through all the rigmarole of the cinematics and stuff. If the boss is knocked out, then don't do any of this stuff. You can think about this as a simple if statement, right? If this condition is met, none of this will happen. It's an inverse if statement. If we have these conditions being met, this stuff just doesn't exist. It does not happen. It's completely skipped. However, on a post-test loop, this will always happen at least once. So if you have that big cinematic that you've been working on so hard and you want your character to see it at least once before they knock the guy out, then you will use a post-test loop. This will always be run once and then it will drop out. So these are the three primary types of loops: while, do, and for loops. Now, as I say, while and do sometimes change how they work, but which is why I'm using the phrase pre-test and post-test loops here. Or I should have a little bit earlier. But anyway, yes. Now, most loops can be broken using what's known as a break command. This is a break to step out of the loop to step you away from the thing. Structs in object-oriented programming, we won't do many of these in our thing, but structs are where we can construct objects for us to actually work with. Pascal doesn't involve structs, but one thing that it does have is functions. This is where we can take a piece of the code and we can put it down somewhere else, and we can look at it and call it as if it was a variable or through a variable. So it's where we can split our code up into bits, and we can then put those bits in different places and helps us with our testing and such. So if you have a really, really long program, you have a really complicated program, you can break that up into 50, 60, 70 bits. And then as you're testing and going through and you know that this bit works in all your conditions, you can simply nullify that and nullify where it goes in the code, and you can put some alternative thing that you know will work for the next step, or you know will be necessary for the next bit. That's important for the reusability of our code, and we will come to a lot of that when we get to our programming stuff. So those are the fundamentals of programming: variables, if statements, and loops. In our Pascal, of course, we have something called switch statements, which we'll come to when we get there. These are where we can make more complicated decisions, giving a list of things rather than simply two options. But we'll come to those as we get there. So if I minimize these. Now, getting started in our Pascal programming. Where are we going to get started? Well, first thing we need to do is we need to get the software. Some of you were not in school the week that we gave out the software. This was now 3 weeks ago. It was a school week, so I don't know why a couple of you weren't there, but where do we find the software that we need to use? Well, we can go to our Google search, open up a simple Google search and type in Windows, and I've already got it there. Windows Free Pascal. And if you put an L on the end and not a K, you'll find it work properly. Now, the top option or top link should be sourceforge.net. This is the best option to get Windows Free Pascal. This is a free program. You are not breaking any laws by downloading this. This is designed as a free source code editor and compiler for programmers. You can go simply here and click download, and a download option will start after you see a few seconds because they want to make some money from ad revenue. Now, Windows Free Pascal is an IDE. It's an integrated design environment, which means that it includes both a compiler and an executor for your code. So it puts all of that stuff together. It's only small. It's only 4.6 megabytes. but I have downloaded it. Now, this is where we might get a tiny little bit tricky because every computer will be different. My computer has 2 hard drives, for example, but typically if you go in here into the downloads folder, you will have a WinZip here called Windows Free Pascal. And I am trying to turn on, yeah. So if I do that and then Windows Free Pascal, that is where you will find your software. So the easiest thing to do here is to simply extract it, right click and extract all. We're going to extract it straight to this location because that way we've got the folder right where we want. And as you notice, it opens the folder for us. So in downloads WFP, there is a folder called WFP. Now, Pascal is a older language and it doesn't treat spaces in files or in file structures at all well. It really, really doesn't. So what we want to do with this is we want to put it in the smallest possible file structure limit. What I have done, and I will show you this. So if we go into this, we'll see there's 3 files, and that's okay. In this simple spot, I would right-click and cut this folder from this location, and I would go into my C drive where I have already created a Pascal folder. And in here is where I would paste it. And you can see that I've already done that. So I would have this as a pasted folder in there. So to be able to access this folder, I would need to simply type C drive Pascal. Inside of this, you will find your 3. There will be 4 files as soon as you've run it because there's a config file, but you will find your files. To open it, you simply double click on this WFP program and it will open for you Windows Free Pascal. And in here, we can create ourselves a new program, the same as you would in any other particular environment. And we can open our system here. Now, when we save our files as well, and I'll end on this note, when we save our files, we need to make sure that our files are saved in a spot where there are absolutely no spaces in either the file name or the directory tree. What do I mean by the directory tree? If I go here to File and Open, because I'm not going to save, but it would work the same for Save As, I go back into my thing, and I have here one called Pascal. You can see that the path for this will be using read.pp in our exercises. Now, if I go back into my folder structure, and I show you this by going to right-click and Properties, you can see that the location is C drive, Pascal, exercises, and then it will be using read.pp. There are no spaces in these. This is not C drive Pascal space exercises. These are slashes. There are no spaces in the file path at all. That is very, very important because as we discovered, to my eternal shame, thank you, Miss Armstrong, that apparently Pascal does not at all like file names that have spaces in it. When you have got that up and running, you can then start coding. Now, the programming language, the programming files are already up on Google Classroom. You can access them there. You can look at these things. I beg you, please don't just copy and paste these things. Don't just copy them in. Read what you are looking at. Look at these different things and say, why is that integer there? Why is that semicolon there and not one there? What is missing from these? In the first one, I remember I gave you this without a semicolon there and everybody freaked out because the whole thing didn't work, right? We have to look at these and read these pieces through. So these Pascal programming exercises are up on the board, on the Google Classroom now. You can access them in your own time, and I will leave you to do that. And I will step you through how to use these different things as we go. So that will be the next video that I will make. For now, the other thing I will show you here is when you have a program up and running, this is the using read program that we did together. To make this work, there are 2 options to making this work. I wish I will actually minimize this because I don't want you to see my ugly face where you want to be able to read stuff. Down the bottom here, this is where our compiler errors and such will be shown. So if we go here to Program and Compile, this down here shows us that it's trying to execute this program. Its debug as a read count is 0, and it was completed successfully, condition 0. Conditions, zeros like this, are the old school way of saying, if everything works fine, give a 0, give a false reading. Is there any errors? False. It took 1.13 seconds to actually execute this, and it's all fine. If, however, I delete a simple semicolon, we want to see a programming error, we can go compile here, and you'll see here that down the bottom it says, using read has a fatal syntax error. This is where you get information about the errors. There's a fatal syntax error as a semicolon was expected, but instead an identifier read line was found. So it expected a semicolon, but it instead found a word. Fatal, this compilation was aborted, so this did not compile, and it took them 152 milliseconds to do. And you'll notice it says compilation failed, condition 1, condition true. There is a compiler error. So that's where you will actually see your compile errors when you have problems, when you have issues. And if you want to if you don't want to worry about just hitting compile, you can just hit run, and all things being equal, you will have your program popped up. So your program will actually open up like this, and then it says enter two numbers ended by a space, so I can put 15 and 58, press enter, and there's my program. That is exactly how this program is supposed to work. It has done that successfully. I didn't want it to run again, but this is how that program is supposed to work, and you can see there that this is it. So that's how you will test your code. So this has been an introduction to programming, flowcharts, pseudocode, the IPO charts, and introduction to how to set up your Pascal to this point. From this point, when you write a program like this, I want you to also write out the pseudocode, the IPO chart, and the flowcharts. I want those three made up for each of these exercises as well. That's very important because your first assignment will require you to do that as well. Your major projects will require you to have these charts put together, and they will be in your exams. They have been in every HSC for the past decade. I know because I did the HSC a little bit over a decade ago, and I did them in the HSC. So these are things that will be there. These are things that I want you to get used to, and these are where your primary focus should be. As I go through, I am working on more exercises for you. I've put a couple more up, and I will keep adding to them. Please feel free to find your own ones, and if you find some good ones, post them up for everybody else to do. Don't hesitate to start getting the conversation going. If there's anything that you need, you can contact me by email or on the Google Classroom. I'm Mr. Boyce. See you in the next video.